In this video, we're going to have a look at the applications of integration. Specifically, we're going to start by looking at the relationship between anti-differentiation and differentiation and how they relate to each other. Then we're going to look at how to find the area bound between a set of two or more curves. And finally, we'll look at what the area under a curve even means. Enjoy. All right, let's make a start. So this class is going to follow on from last Tuesday's stuff, which we had a look at some of the fundamentals of integration. We're now going to look at how to apply our understanding of integration to some of the more complicated style questions, or even just more so those extended response scenarios. A couple of things we look at, namely the relationship between the derivative and the antiderivative, how those two play into each other and can be used to solve more complicated questions. We look at how to find the area bound between curves rather than just bound between one curve and the x-axis. And the final thing is that integration can also be used for finding the average value of a function. So kind of like how you do averages in real life, how you would add everything up and divide by a number of things, exact same sort of scenario here, but we use integration for it. Okay, first up, we look at what's called integration by recognition. This really leverages the fact that the derivative and the antiderivative are like reversals of each other, where if I anti-differentiate the derivative function, I get back to the original function. That's the whole point. This is a kind of question, I think I actually pulled this from a past exam specifically, like word for word, and it was, we have the derivative of x times sine x is equal to this, and we're supposed to use that information to find the antiderivative, or the integral, of x times cos x. So normally, we can't just find that antiderivative, right? If you look at the rules of integration, the table of known integrals, which I've since updated a little bit to discuss a bit more in detail what's up with that hyperbola. But anyway, if you look at all the things in here, none of these have a product of functions in them. It's always just function or, at worst, a composite function. Nothing in there screams product of two separate functions. So we have to rely on alternative methods. These questions you'll be able to identify pretty quickly, in the sense that you'll have some derivative given to you, and you'll have to find some integral, or maybe the other way around. You have some integral and you have to find some derivative out of that. Although I'd be shocked if it was the other way around. A lot of the time it'll look like this. The first step of this is always to anti-differentiate both sides of your derivative function. So you slap an integral sign onto both sides. So you integrate on this, you integrate on this, and that's what this bit looks like here. Now, whenever you anti-derive the derivative, you get back to the original function. So that's why the derivative and antiderivative operators cancel out, leaving you just with what was in the brackets, x sine x. And the right-hand side, well, we can deal with that in a little bit, namely to split up that integral. We have a plus sign between these two things, so we can split them up into individual integrals. Now, what's worth noticing is that when you do that, that is the integral that we're trying to find. We want integral of x cos x. We've got it in this equation, and it really matters that it's in an equation specifically because that means that if we were to rearrange this, say by subtracting sine x to both sides, or rather the integral of sine x to both sides, you have an equation that says, hey, the integral of this thing is equal to that right-hand side. So instead of having to do any anti-differentiation, at least on this function, all I have to do is simplify this right-hand side, and I'll be fine. From there, the integral of sine x does just go to cos x, and because it's negative, we're going to slap a negative sign back on that. And so, so the integral of sine goes to negative cos, and because it's negative, you double negative it up, which is why it goes back to being a plus. You put a plus c there because this was the indefinite integral. There was no like terminals on there, so you don't have to go any further. You just put your plus c. It's a pretty common kind of question. You'll find this in the multi-choice section of a TechActive exam pretty often. Or if not, it'll be, no, in fact I've only ever seen it in multis, I think. Anything to clarify about what's going on there? Next up, area bound by two curves. So one of the things we explored with the definite integral is that if you do the definite integral, you're getting the area underneath a curve. So if we go all the way down here, if I just do the definite integral from 1 to 4, I'm going to have some negative portion of the area and some positive portion of the area. The definite integral just says this minus this. That's all it really does, whatever those areas are. That is effectively finding the area underneath a curve with respect to the x-axis. So if the blue line's above, it cuts off at the x-axis. If it's below, it still cuts off at the x-axis. What we look at here is, okay, instead of worrying about the x-axis as one of the boundaries, we want just the curves to be the boundaries. So I want to figure out what this grey shaded area is. Now, one of the ways that you can handle that is by following more or less these steps up here. First up, just figure out what lines or curves contribute to the perimeter of your area. So in this case, you can see the entire thing is totally bound up by G and F. Right? If you were to trace around this grey bit, the entire perimeter of the shape is totally made up of the red line and the blue line. So those are the only functions that we're going to care about with our for this approach. Next up, we want to find the endpoints of the bound area, more specifically the domain of the bound area. So we want to figure out horizontally how far does this span. And if you have a look horizontally, you'll find that in this case specifically, it'll be the intersection points between the two functions. We'll see another example where that won't necessarily be the case, but in this case it certainly is. The horizontal span of that area is from the two intersection points. So in order to find those, you would do it like you normally do to find any intersection points between curves. You just grab function 1, equate it to function 2, and then solve for x. That's what this is here. Bang, bang, bang. CAS question, so unless you're able to quickly find that there's factors of -12 and 18 in here, then best off just leaving it to either quadratic formula or, if you can, CAS. These are often CAS questions, so a lot of the time you can just go and get away with doing a solve. So basically what we just found is that this spot here is -12 and this spot here is x equals 18. Okay, so we found our interval. From here, what we want to do is figure out which of these curves is on top and which of these curves is on bottom. So what that means is effectively what function is above the other function as far as y values are concerned. So if you look at specifically g of x, everything underneath g of x would be highlighted in blue there. Everything underneath f of x is highlighted in red. And so you can see it's missing that grey area there. So if you compare the two things and you think, okay, since g is on top of f, you can think of g as like the total area of what you're working with. You've got this big block of blue. To find the bit in the middle, what you'd want to do is subtract all this stuff on the outside, get rid of it all. What we notice is that anything underneath the red line is all that stuff on the outside. So if you consider just wanting to find that middle, you would simply do the area under G minus the area under F. Or in other case, top take bottom, because it's G is top and F is bottom. And so you literally just chuck that in exactly as described. Specifically, you would chuck the domain that you found from earlier as the boundaries of that integral, because you're doing area of top minus area of bottom. It becomes area because you're chucking it in a definite integral. Anything to clarify as to why that works, or is that fair enough?
Chris, could you show me how to do like the calculus functions on the CAS?
Yeah, certainly. Cool. Let's get that up. So on the CAS, which one do you use? Oh, I'll do both, I guess. So starting with TI Nspire. on the calculator tool, a couple ways you could do this. So for derivative, which we haven't done here, you could do shift minus to get up the derivative operator, or you go menu for 1 for derivative, that'll get the exact same thing sorted. For integral, which is what we want to do, it could be shift and then plus, so shift button and then the plus button. And from here, plugging in the terminal shouldn't be too challenging, right? You put in your negative whatever, your positive whatever up there, and the function in there. You just do dx, or whatever variable you're doing the integral with. The other spot for it is in, again, the calculus, so menu 4, and then 3 for integral. Exact same thing. So if I were to specifically do this example again, I'd go -12, I'd go 18. I personally would have defined the functions earlier rather than write them all out one at a time in here. So maybe, yeah, I'll kill that. We'll go g of x, what's g? G of x is equal to half x plus 18. Oops. And then we have f of x is equal to x squared on 12. And then once again, you bring up that, bring up that integral operator, either by shift plus or by the menuing. We wanted it from -12 to 18. And then you would do g of x minus f of x. And it's going to give you that number there. If it's unitless, you don't have to necessarily say units squared. They do allow just having the value there. Although if you did say unit squared, I could imagine that being slightly more favorably looked upon. So all that to say, either is okay. Anyway, that's that, Kaz. As for the other one, I don't believe many shortcuts necessarily exist. I think you just have to go through the menuing after the keyboard. So keyboard, let's see if I can spot it again. Probably math, yeah, math 2, and then this one here. You click that, it's the exact same thing. You put your terminals in. If you don't want to have any terminals at all, like for instance, if I just wanted to do antidiff of x squared, you just leave the terminals blank. It's the exact same thing with the TI Nspire. Yeah, so that one's math 2 there. All right, anything else to clarify about how that all works? Sweet. Okay, so that's the gist of what's going on as far as finding bound area. Now, one of the circumstances that could come up is that your curves cross over. So effectively what's happening is that the function that is on top will not necessarily stay on top for the entire interval. Functionally, all we're really doing is the exact same procedure, but we're going to do two versions of it. One version where one function is on top of the other, and the other version where it's the reverse situation. So we'll see what that looks like. In this case, this was also an exam question. This was find the area bound between the inverse and the function. It wasn't written exactly like this. I've just filled in the blanks of what you would have done in the previous like part A, B, C sections. So this is a kind of thing that really follows up on the extended response side of these questions. So I've just filled in the blanks of what those would have been, but these would have been answered previously. So we have our two functions and the line x equals 1. That's a pretty important part. If it was just the two functions, bound by the two functions, it would be talking about this area here. However, because the line x equals 1 is also mentioned, we're actually looking at all of this, all that grey area there. So, step 1, identify everything that contributes to the perimeter. We've got some red, we've got some blue, and we got the black line, x equals 1. So that tells us that everything important will be contained within those three lines. This was a tech active. I said it was in the extended response section, so getting a quick sketch of those pretty easy to do. Even tech-free, right? Like tech-free, this is just a quadratic with a restricted domain, and the dilation factor doesn't really matter on the root. So you could very quickly just draw a root and half of a quadratic and get a very similar effect. Okay, next up, endpoints of the bound area. So specifically the domain. In this case, there's no solving to be done here. This is a case where it's clearly cut off by x equals 1. And I mean, if you wanted to, you could solve for this spot x equals 0 here, but if you know any... Oh, damn. I didn't... That's supposed to be the quadratic. Rip. Alright, I'm going to write a note for that. Fix f inverse x quadratic. That is supposed to be written as a quadratic. Okay. But yeah, if you know anything about quadratics or square roots with no translation factors, they should start at 0. So our domain is going to be 0 and 1. From here, we want to identify the crossover points specifically. So there's a portion here where red is above blue, but there's also a portion here where blue is above red. So all we're going to do is solve each of those sections individually and then add the results together. But we need to know when it actually crosses over. So once again, the way we do that is by equating the two curves and then solving. Again, you could do this tech-free if you wanted to, although it is tech-active, so just use the solve function. That crossover point is therefore x equals a half, so we're going to have two separate domains, one from 0 to half and the other from a half to 1. From there, you want to figure out which one's on tops and which one is on bottom. So I've just sort of color-coded what each of the domains and integrals would be associated with. It's basically what I said before, which was the f of x is on top and f inverse is on bottom for that first bit, which is why we do f minus f inverse for that first bit, and then it changes. So for that second section, from a half to 1, you see instead of putting an f there, you put an f inverse. Instead of putting f inverse, you put f. It's because the top and bottom have been reversed. So all in all, as long as you're following the rules of top curve take bottom curve for that specific domain for which they are top and bottom, then it'll be sorted out. This would be another thing that you just plug into your CAS, although, yeah, technically you can do this tech-free. Unlikely for it to... I mean, you'll get a question like this in tech-free, but not with these kinds of numbers usually. That's only a slight nuance as to how you handle that. Anything to clarify further there? Oh, actually, I've got one. It doesn't matter where this curve is. This could be in the first quadrant. It could be even all the way down at the bottom. So if I draw just some random whatever curve, or set of curves, rather, on the handwritten section, let's say we have quadratic, let's say we have linear, and I want to do it from, let's say, here to here. I want all of this. So this might seem weird to do. You still just follow top take bottom. That's the rule. Doesn't matter if it's below or above the x-axis. The fact that you do top take bottom will always account for wherever it happens to be on the graph. So if this was x equals 1 and this was x equals 3, you would do your integral from 1 to 3 of linear minus quadratic, because linear is on top for the whole thing. Sorry, never mind. There's another crossover here. Let's say that crosses over at 2. Linear minus quadratic for 2, and then quadratic minus linear for 3, for 2 to 3. So it doesn't matter where it exists on the curve, you're always just doing top and bottom. Alright, that's all the area stuff. The last thing we look at is how to do average value. So this is where you're finding, like for example, if I draw another thing real quick on the handwritten notes, if I were to draw, circular function, right? We kind of already know circular functions always oscillate plus minus some mid-level. that mid-level would be considered the average value of the circular function. Now, that's pretty quick to find for circular functions. It's just the vertical translation, not necessarily so quick for other types of functions, and even more complicated if we change the domain up. Like, for example, if I only wanted to look at the average value from here to here on the handwritten bit, it's not going to be this horizontal line anymore. It's going to be somewhere like there-ish, a little bit up and a little bit down of the peak and trough there, or the max and min there. So this formula here that's on the notes is where you can do that for any function over any domain. So what do we actually do? Well, we need to identify the function that we want to take the average value of. That's a pretty quick thing. You want to find the interval over which you want to evaluate the average value. That's going to be your A and B values. And well, all you do is just sub in at that point. If you have A, B, and the function, that's all you need. This one I borrowed from another past exam, written more or less the same. This did come with a picture, but I thought it'd be nice to see how you'd go about it if you didn't have a picture along with it. And it's simply just to calculate the average value of a circular function over a specific domain. So we don't quite get a full cycle, which would mean that the average value isn't quite -1, as you might expect, because of that offset domain. It's going to be a little bit different. Pretty quick. So this is the function we care about. Nice. This is the domain we care about. Nice. Therefore, A is going to be the lower bound, B is going to be the upper bound. You plug and play. There's really not much going on here. These average value questions are pretty much always going to be tech active. And so as long as you're able to identify the interval and the function's usually the easiest part of that. Sometimes they might make you solve the interval. But usually this is like a quick one marker, like, hey, find the average value of something. And I'll chuck it in like a step 7 of a 7-part question in the external responses. Anything to clarify there? One other thing that's interesting about doing the average value is that you don't necessarily need to use integration all the time. In fact, there are certain circumstances where you wouldn't want to use integration, namely because identifying the function is either impossible or just not worth your time. The only thing we have to recall is that the definite integral is always just the area under the curve. That's all it ever is. So by whatever method you want to find the area under the curve, you can use that, as long as it's valid, right? One of the ways you could do that is just through geometry. So it effectively just comes down to, as long as you know your interval, and you can find that area through some means, really it's just find the area and divide through by the interval. This comes in handy for specifically this multi-choice question. You absolutely could find the value or the rule of h of x, right? You've got enough points on this graph to figure out the equations of 2 straight lines. You could integrate that. It's kind of heavyweight though, not really worth the 1 mark of the multi. So instead, realize that we can break this down into 2 separate shapes, specifically in this case a triangle and a rectangle. All we're going to do from there is figure out the areas of those triangles and rectangles. Pretty chill. Area of triangle, half base times height. Area of rectangle, length by width. Just keep in mind the actual values of these coordinates here. If it spans from 1 to 11, that's a length of 10. And in this case, it'll be a height or a width of 4, because it goes from 0 up to 4. Don't get tricked by this coordinate here. This is not a height of 10 for the triangle. It's a height of 10, but minus 4, because it's already been shifted up by 4, if you look at where the triangle is actually situated. So as long as you're keeping your coordinate geometry in mind, offsetting those values, you'll be sorted. So you get the area of each of those individual shapes, add them together, and that tells you area under a curve is going to be 70. all you do to complete the average value equation is to divide through by the length of the interval. In this case, the interval is from 1 to 11. Remember, we always look horizontally for our interval. You can think of it basically as just domain. That's that. Anything to clarify there? All right, last thing up, which is probably one of the weirder things. What does the area under a curve actually tell you? Doesn't always just mean area, although some external responses certainly do it that way. One of the graphs I came across in the book, in the Cambridge book, was this one here, which is a bit of a weird graph. It's supposed to be dt on d capital T, where little t is time and capital T is temperature. Usually you have it the other way around, which is you have a temperature function and it's written in terms of time. This one was kind of the opposite way. And it was done opposite to sort of prove a point. So in this case, we're observing the area between 35 and 120. Now, if you remember what our x-axis is, our x-axis is temperature, because capital T is for temperature here. So from 35 to 120, that just means temperature values of 35 and 120 respectively. If you think about how you grab this area, the first thing you do is, well, you would do definite interval, which means you have to anti-differentiate. So one of the things that comes about is if you anti-differentiate this function, you get little t of big T, right? If you have derivative and anti-derive the derivative, you get back to original function. So if little t is a thing on the top, kind of like how if you have dy on dx and you anti-derive that, you get back to y. If you have d little t on d big T and you anti-derive this, you get back to little t. So that's this one here, little t of big T, the time for any given value of temperature. So from there, once you've done your antiderivative, you would just plug in these values. So you plug in 35 and 120, both of which are, as we discussed earlier, temperature values. So really, what we've just effectively done is we've said, what's the time at temperature 120? What's the time at temperature 35? And then subtract the two. Or, in essence, what's the time between temperature 120 and temperature 35? So in this specific circumstance, the area under the curve for this domain tells you how long it took for the temperature to go from 35 to 120. Complicated. Do I need to explain anything else in any more detail there? It's a tough one, I'll say that much. Not super necessary. It might be like a one marker on either an investigation stack, sometimes called an application task. Could be like a little dot point there, or it could even be a one marker on an extended response, like, hey, what did we actually just find? That's about it for applications there. There's a nice little summary there if you want to print those off for your own sake. Otherwise, anything left over from what we've discussed or otherwise you'd like me to clarify? Because otherwise we'll get into some questions. Okay. The first one we'll do is we'll have a look at that first kind of scenario where you've got a derivative antiderivative relationship. So I'll do a screenshot of that whole thing. I'll put that in the chat so you can refer to that, and we'll try and do one of them live. So that'll be, let's say, yeah, this one we'll do 3B. 3B in the chat. Have a think about what you'd go and do. and either try that yourself, or we can do it live if you like. Either way. Maybe one thing I'll start by doing is saying like why that is the way it is. If you've got differentiate and anti-differentiate in the same line of text, it's going to be this kind of question, right? Find derivative of this and then use that information to find an antiderivative. That's why it's this kind of question, integration by recognition. Even if you don't see the derivative operator and an equal sign, still the same sort of thing. If you're running into issues, let me know. We can do this one live if you like.
Chris, I'm a little bit stuck, but I did find I did find the differentiate of like sine x over cos x.
Yeah, yeah. Oh, so you did 3a then?
Oh wait, sorry, 3b, I mean my bad. Cos 2x over sine 2x.
Yeah, so you did the derivative of this then?
No, yeah, I found the derivative of that.
Yeah, alright. What'd you have for that?
I got negative sine, I mean, sorry, negative 2 sine 2x over 2 cos 2x, which I simplified to negative sine 2x over cos 2x.
Negative sine 2x over cos 2x. That's a bit off. Did you use quotient rule for that?
Oh, yeah.
Okay. Let's go through that then. So quotient rule. So how do you start off quotient rule? Or how do you what do you start off doing to find derivative of cos 2x sine 2x?
You establish a u of x and v of x.
Yep. Which one's which?
Um, Cos 2x is u of x, and then sine 2x is v of x.
Yep. That's good. And then from there, derivatives of each. So what do you get for those?
Um, well, cos 2x, I got negative 2 sine 2x.
Mm-hmm. And then v dash.
And I got 2 cos 2x.
Yeah, that's good. And then for quotient rule. So that is, we're looking for, dy on dx. You do your cross still, but you put a minus sign between them. So you do sine 2x minus multiply. Yeah, multiply by minus 2 sine 2x. Wow, really butchered this one, huh? Let's fix that up. Sine 2x minus 2 sine 2x. And there'll be a minus sign between the product of these two. So 2 cos 2x and cos 2x, so you could just say cos squared x there. 2 cos squared x. And then all of that over v squared. So sine 2x all squared. Did you have that? Or more or less that?
Chris, at the numerator at the very end, I had negative cos squared 2x.
Negative cos squared. It should be a 2 there because you got 2 times both of these. But yeah, there should be a 2x in the brackets there as well. But yeah, there still should be that coefficient of 2 at the front because of this coefficient of 2.
Yeah, right.
Oh yeah, but otherwise that's fine because then you just continue on. Sine 2x into this, you're going to get that sine squared once again. So negative 2 sine squared 2x minus 2 cos squared 2x. That's all over sine squared 2x, which is one of the issues we're having is that we want this derivative to basically look as close to the antiderivative that we want to find. So specifically, we're trying to find the antiderivative of 1 over sine squared 2x. 1 over sine squared 2x. Now, we have our denominator, that's good, sine squared 2x, but all of this up here, it's kind of giving us a hint, which is that this somehow gets either exactly 1 or pretty close to 1. So does anyone have any ideas how or what potentially could be done to make the numerator up here maybe not 1 but closer to 1? This will be a test of or a revision of your trig trig formulas, trig identities. I guess you'd probably call this one a formula. Specifically, there's one around having sine squared and cos squared in the same line.
Do you make it tan squared?
So tan is when you have sine divided by cos. So I like that you're thinking about where sine and cos is related to each other. There is another one though. What I'll do is I'll oh yeah, no, I see what you mean actually, which is you could probably split this function up into -2 and then -2 tan squared. That does get us further away from making it look like this though, if you were to do that. So that's the only downside there. One thing I'll do to try and make it a bit easier is do a bit of factorizing. This -2, we can take that out the front, and then you've got sine squared 2x plus cos squared 2x in those brackets, sine squared 2x. This bit here, there's something special about sine squared plus cos squared. Anyone remember what that equals? Sine squared plus cos squared?
Doesn't it equal 1?
Yeah, equals 1. Do you remember where that came from?
It's like the Pythagorean identity.
Yeah, exactly right.
Yeah.
We have some triangle. So if hypotenuse is 1 on the unit circle, the y is sine, the x is cos, you have cos squared plus sine squared equals 1 squared, and 1 squared is always just 1. It doesn't actually matter what's in the brackets of the angle, as long as they're the same coefficients inside there. That's all that really matters. So that gives us final answer -2 on sine squared 2x. This is very similar to the antidiff we're looking for. So effectively, we just got this up to the stage where we have the derivative relationship, dy on dx. So if I go back to the screen share, the thing we need to have is a statement that says derivative of function equals something, which we could start writing out now. We started with the function cos 2x sine 2x as a division. So I can say derivative d on dx of cos 2x on sine 2x is equal to -2 on sine squared 2x. That's what we just found. All I'm doing is formalizing that. The second part of it is to say, okay, use this thing to find our antidiff. So we want to find, what was it? 1 on sine squared 2x. So based on what we did in the first example, we have all the information more or less the same as what we had in the example. What was the first step we did? What should we do here? Well, that's two questions back to back. Maybe I'll just say, what was the first step we did in the example written out? Say screenshot and a screen share. On the screen share, I'll highlight the first line.
Split the function.
Yeah, I think that kind of cut out a bit, sorry.
Do we split the function?
So split the function comes immediately after what I've highlighted on the screen share. Beforehand was like, this is where we're at, basically, at our stage. If you look at the screen share, we had derivative of something equal something, and you want to find this antidiff. The first thing we do is antidiff both sides of that derivative equation. So we slap those integral signs on both sides. So that's what we're going to do on our example. So if we go back to the handwritten bit, I'm sure it'll focus. There we go. We slap an antidiff on this and an antidiff on this. Now, by its very nature, antidiff and diff always cancel. So we can kill all that and just leave the left-hand side as that. And all we're left now with is this integral sign that we've got to worry about. The next goal is to try and rearrange this equation to get this in that equation. So we've got to play with a few rules around how you can rearrange integrals. Any ideas on how we can make this integral look like that integral? One of the things you can do with integrals is any constant coefficients that are multiplying the integral. Now, in fractions, it's a bit harder to see that's a multiplier, but it is. It's a multiplier of that fraction by -2. You can actually take that out the front. And so, in doing so, we could rewrite as cos 2x on sine 2x is equal to -2 times the integral of 1 over sine squared 2x. So just like that, we've made these pretty damn close, right? We've got the integral, but there's still this coefficient on there. So there's only one step left to do. What do I have to do to this right-hand side to make the right-hand side now look like that in red? Guess I should have put my dx there as well. Let's be formal. Remember, this is an equation, so you can go and do operations to both sides of an equation to move it around. In fact, to make things even easier, I'll say that this integral is going to be called capital A. So I'm going to say cos 2x on sine 2x is equal to negative 2 times A. So instead of saying get this integral on its own, if I just said get capital A on its own, what do you do now? Like literally only just looking at this line. If I said get capital A on its own, it's currently been multiplied by negative 2.
Divide both sides by -2.
There we go. Divide both sides by negative 2. Thank you. Someone has to speak up. I know it looks like it's all complicated because I chucked integrals in there, but this is fundamentally just doing algebra. Sine 2x, that would be equal to A, but remember that capital A, I just did as a substitute for this thing here, which was the integral of 1 over sine squared 2x. And just like that, without having to actually do any antidiff on this, we have antidiff of this equals that. Hence, we have found our antidiff. So it won't always be just 1-to-1. You won't always just be able to do your integral, rearrange, and that's it. You might have to, I mean, I guess this is also just rearranging, but I guess I meant more so as in you won't just have to like put one thing to one side. You might have to take coefficients out, do some deriving, do some dividing. Yeah, that's the word, not deriving. But fundamentally, at that point, it is algebra. The only thing that might be holding you back a bit there is understanding the rules around integrals specifically, how they can come in and out of the integral sign. Okay, so we'll do another one of those just so we can make sure we've got that one locked in. The procedure is the same. Let's see. So we'll do 3C this time. 3C, which I'll start writing out, and we'll do live together. So y is natural log of 3x squared plus 7, and hence evaluate. I'm going to get rid of the. Well, no, maybe I won't get rid of the terminals. It'll be worth revising how that works. Integral from 0 to 2 of x over 3x squared plus 7. So first stage, we were told to find the derivative of this. What I'll do is I'll get the derivatives tables up if you're not familiar with those. But otherwise, have a think about it. Okay, rules for diff. I'll get a screenshot of that going. And then, yeah. So I guess the first question to ask is, there's a couple of different rules that could apply to these more complicated derivatives. You've got chain rule, quotient rule, or product rule. What would be applicable here and why? Or even just what would be applicable? Then we'll go from there. let's go down the list then. So if you have a look at the screen share, I've got the chain rule up. Chain rule is when you have a composite function. So if you have a function within another function. Is that what we've got here? Yeah, correct. So the fact that we've got a quadratic, 3x squared plus 7, inside of a logarithm, those brackets aren't a multiplication, those just are natural to the logarithm. Just for a final quick revision, product rule you use when there's a product, a multiply between two things, and quotient rule, as you saw earlier, you use when there's a division of two things. So the way chain rule works, you take whatever's on the inside, in this case I'm going to just call it u, that's going to be 3x squared plus 7 in this case. From there, rewrite our function purely in terms of u. That's going to give us natural log of u. That sets us up. Does anyone remember what the next step of chain rule is? Or does anyone want to read the next step of chain rule from the screen share? Find derivatives. Yeah, precisely. So we got u dash, that's going to be 6x. We've got y dash of u. Derivative of log is always just 1 over whatever's in the brackets, which in this case is the letter u. Now from here, we've got these two results. We do something with them. Anyone remember?
Chris, do we cross multiply with the 4 things that you got there?
Not cross multiply, oddly enough. So cross multiply is only for product and quotient rule. Chain rule is a bit special in that it only cares about these two specifically. So you have your final dy on dx, and it's going to be 6x over u, but remember that u is 3x squared plus 7. And you can kind of use, in this case, because we were told the diff-anti-diff relationship, you can kind of use this to guide you. It's not going to be exact like we saw earlier, but that can kind of give you an idea of what you should end up with, more or less speaking. Though, I guess to be fair, we did have this last time, which looked nothing like it, so maybe that's not necessarily the best advice. But yeah, chain rule is just multiply derivatives together. And these are all on your formula sheet, by the way. You guys don't have to memorize that. As long as you can, like, if I point your attention to the screen share again, like, as long as you can read that notation, dy on dx equals dg on dx, dy dg, I think the formula sheet uses u instead of g, but as long as you can read that notation and know what that means, then that's all you need. But okay, so we have our derivative found, which means we can write out our relationship now. So we can say that the derivative d on dx of the natural log of 3x squared plus 7, 3x squared plus 7, is equal to 6x on 3x squared plus 7. We have that diff relationship, and we're told to use that to help us evaluate integral 0 to 2 of x over 3x squared plus 7. So with that in mind, does anyone remember what we did last time? What do we do to start this off?
Chris, do we have to integrate both sides?
Yeah, integrate both sides, precisely. Yep, when you integrate both sides, derivatives cancel. So that's why we can get rid of this operator on the left. And then what we're going to do, I'll draw it in red just so it's better contrast. We'll just chuck an integral sign on that. Sweet. All right, so we have our equation that we're working with. That's that left-hand side. And the thing we're trying to get is this thing on the right-hand side here. For now, I'll knock the terminals off just so that's not confusing just yet. We'll put them back afterwards, but for now, if you just wanted that, what do you think you'd have to do? That being the red.
Because on the left side function, right?
Mhm.
I can see that the only difference between the the 6x over 3x squared plus 7,
Yep.
I can see like the only difference between those two is that the one has like a multiplier of 6. So can you take that out of the front of the integral?
Sure can. Yeah. So that's going to be natural log 3x squared plus 7 is equal to 6 times the integral of x over 3x squared plus 7. Nice. Pretty close match. Almost there. The integrals match, but it's not quite on its own yet.
Can we divide both sides by 6 now?
Divide both sides by 6. Absolutely. So finally, we have 1 over 6 natural log 3x squared plus 7 is equal to that integral x over 3x squared plus 7 dot dx. So if it just said find this, we would have won. However, we were told getting 0 to 2 of that. Don't let that be too confusing yet. If we ignored everything else and I just said we want to find integral a to b of f of x, what are the steps you follow normally when wanting to do that? Just any old definite integral.
Do you look at the area under the curve?
Yep, so it's area under the curve. But as far as the operations is how you go about that, you anti-differentiate and then you do capital F of b minus capital F of a, where capital F is that antiderivative. So one of the things I want to highlight is that this left-hand side is the antiderivative of this. So really, what we've already just done is find our capital F of x. That function there is capital F of x. So if you want to do the integral from 0 to 2, you're now doing capital F of 2 minus capital F of 0, where this thing here is our capital F of x. So because we're about a minute to spare, I'll just continue doing that. You're just subbing in x equals 2 and x equals 0 here. 1 out of 6 natural log of 3 by 2 squared plus 7 minus 1 over 6 natural log of, well, 0, so 7. And then 1 over 6 natural log, 2 2s are 4, 12 minus 1 out of 6 of natural log 7, 8, 9, so 19. You can take the 1 out of 6 out as a common factor. Natural log 19 minus natural log 7. When you do a subtraction between logarithms, that is a division. You can replace it with one logarithm with the same base but divided. So 1 out of 6 times natural log of 19 on 7. You could go further with this if you wanted to. You could bring this in as the 6th root of all of that, but that'd be a bit whatever. That would be your final answer if you were doing just well, taking it a step further to do definite integral of that. So, if anyone wants me to clarify that any further, feel free to stay behind. Otherwise, this is officially end of class. And have a good day.